Hey everybody, we've been getting a lot of questions on Spectronaut and some of the DIA-based proteomics techno jargon babble that's very common in this field and in the software we use, and it's it's like a real problem. Like there's a lot of this that's just really inhibits the field, and proteomics is filled with techno babble, and so I'm trying to wanted to make a presentation on where it comes from, and maybe it would help understand some of this stuff, because a lot of times I have to refer to this too. So there seems to be a lot of it, and there's more every single year. So let's go see where this techno babble comes from. Okay, so different programs will sometimes define these a lot differently. It's supremely frustrating and confusing to everybody. So even to me and the people in my lab, and especially the people we collaborate with who haven't been doing this for a long time. So let's look at some of the specific techno babble. That's some of it's specific to Spectronaut, some of it isn't. Most of it is. So I'm doing this so when you receive your Spectronaut results from us, it gives you a little better understanding of what these what this stuff means. Okay, so let's start from the top. The first thing is PG. You'll see this on your Spectronaut reports or in the software, and this refers to protein group. And just a reminder, the difference between a protein group and a protein is that, remember, we digest proteins into peptides, and oftentimes those peptides can be in more than one protein. And especially when you're analyzing thousands of proteins at a time, often it's not feasible to say these group of proteins belong to this group of peptides belong to this specific protein. So we do our best, and when we can't tell exactly what protein we've identified and quantified, we call it a protein group. So a protein group may contain multiple proteins. PP means peptide. EG equals elution group. That's kind of confusing, but I'll explain where that comes from in a minute. FG stands for fragment group. We don't usually use this in our lab, so you don't have to worry about it. PTM, of course, is post-translational modification. XIC is extracted ion chromatogram. I'll explain what this is in the next slide, or in a couple slides from now. AA or AAA is amino acid, could also be a battery, but in our case it's amino acid. RT is retention time. IRT is indexed retention time, and I have a couple videos in my video playlist that explains what indexed retention time is. It's almost magical. IM equals ion mobility. I'll explain what that is, and I have a couple presentations about that too. Precursor, this is important, and I'll explain what precursor is in a couple slides from now. DIA, of course, is data independent acquisition. It's kind of really stupid. It's, that's, basically just think of it as mass spectrometry for proteomics. Uppercase M or lowercase m is mass. Z is charge, which is basically the number of protons stuck to a peptide. M over Z is mass overcharge. Remember, this is the one we actually measure. M plus H is mass plus the proton, and this is a little confusing because back in the day we couldn't tell the difference between a hydrogen and a proton, so that extra electron was too much for most mass spectrometers. Now we easily can, so we call that M plus H. Adjust my camera a second. Okay, MS1 is the intact mass of a peptide ion. MS2 is the fragment broken off the peptide ion, and I'll give you some slides to explain what that is. Okay, so in order to kind of understand, once you kind of understand what the mass spectrometer is really doing, it makes this a little easier. This took me a long time to understand, so don't worry if you don't understand it right away. So we actually measure ions. For proteomics, these are usually peptide ions that contain 1 to 3 peptides attached to it. 1 to 3 protons attached to it. All right. So not surprisingly, people are still trying to figure out how this actually happens. So the actual electrospray process, John Fenn got the Nobel Prize for in 2000, I think it's 2001, maybe 2002, I don't remember. So anyway, before electrospray ionization, one of the only ways to get peptides into a mass spectrometer was to heat them up at an incredible temperature, maybe like a couple hundred C or something. And as you can imagine, this turned them all into carbon. There were actually some ways to do this back in the day, like fast atom bombardment, or what was called a moving belt, which I actually saw in my lab at Michigan State. They actually had the pieces for that. So if you want to Google search moving belt, that would be you and like 3 other people will actually have done that. And this is just from that paper. There's different competing mechanisms of how these ions are formed, but basically you have a droplet of liquid. This will have an acid in it. Usually for this we use formic acid. And then some magic happens that this paper tries to figure out what kind of what mechanism, how it works. But essentially after 75 or so nanoseconds, you end up with a peptide ion with some proton stuck on it. Okay. So anyway, you get a peptide with protein stuck on it in the gas phase. So remember, all of us in biology, we're all working with liquid. So we have to take whatever's in the liquid, put it on the gas phase, and that's the ionization process. And this is actually what we measure. So we measure peptides with protons stuck on them. And this is important because mass spectrometers don't measure mass. They measure mass over charge, or mass divided by charge. And as you can imagine, like the same peptide with multiple different peptides on it. Let's see if I can get my cursor working. For example, let's say this is a peptide with 3 protons on it. This will have the mass plus the protons divided by the charge. So m plus 3h divided by 3. And this would be m plus 2h, or 2 protons divided by 2. And then the mass over the charge 1. So that would be the mass, or mass plus the proton. So you can imagine these will actually have different mass over charges in the mass spectrometer. Okay, so this is an important part. This is the LC part. So all we do in the lab is liquid chromatography tandem mass spectrometry. None of this would work without the liquid chromatography part. And actually, this is responsible for a lot of the performance gains that we've gotten over the last 10 years. So basically, we have these machines. They're either called HPLC, or high performance liquid chromatography, or more aptly known high price liquid chromatography, or UPLC, which is ultra high pressure liquid chromatography, which is basically high pressure liquid chromatography at even higher pressure. so usually these are at, they can go up to 20,000 psi, which is actually higher pressure than like at the bottom of the Mariana Trench or something. Like, it's an extremely high pressure. But remember, the columns are really small, so it's not going to blow up like a pipe bomb or something. All right, so as the peptides come off of these columns, they form peaks. So the peptides come off the column and they start eluting, and they form a characteristic, what we call peaks. And you can see sometimes they tail. They're not supposed to do this. They're supposed to look kind of Gaussian, but because everything's not perfect, they kind of tail over time. So these are, when you think of peaks in an LC-MS system, this is actually what we're talking about. Okay, so each peak contains lots of ions, and we measure all of them, and we measure them all over time. So think of the mass spec as a detector that's sampling peptides that come into it up to like 300 times a second. And all of these ions, they go up in intensity, so we can put together all of these scans to form a peak, and each one of them have different number of ions. They all have a lot. And then after we measure them, we either take the area or the intensity under these peaks, and we quantify them in various very clever ways that people come up with. It's sometimes not a simple process. Okay, so as the peptides enter the mass spectrometer, or after they enter the mass spectrometer, sometimes before, but you don't want it to happen before. Sometimes once they enter the mass spectrometer, they are fragmented, and those peptides will fragment in predictable ways, mostly, and give you fragments of the peptide that will have different masses depending on where they fragment. And usually this fragmentation happens at the peptide bond under the collision-induced HCD or CID, the collision-induced dissociation. So for example, this peptide will fragment into fragments of the original peptide. And down at the bottom on spectrum, usually this is at the bottom, these are the intact masses of the peptides. And all peptides have isotopes. And this isn't a different presentation, but I'm not really going to go into mass spec isotopes now, even though they're super cool. So if a peptide fragments in the mass spectrometer, because it's the same molecule, it will have the same retention time and the same peak characteristics, although the masses of those fragments will be different, but they will have the same retention time, they will look the same, and they will have the same ion mobility, which I will show you here. So again, these elute in time. This would be the intact mass of the peptides. These are the fragment ions. And you can see because they're from the same molecule, they elute at the same time. This is what Spectronaut calls elution groups, because they're groups of ions all eluting at the same time. Pretty clever, huh? I don't know. I don't know if anybody besides Spagnosis calls them elution groups, but I guess it's pretty apt, so that's kind of cool. Okay, so ions also have the same ion mobility if they are from the same molecule. And I have another presentation on this, but ion mobility is basically, think of it as a wind tunnel, even though lots of different ion mobilities work a little differently. This is called a trapped ion mobility. So peptides that have the same mass can have a different shape. For example, if the PTM, so like two different isomers of a peptide or isoforms of a peptide that have PTMs on different amino acids. So think of like, for example, a phosphopeptide. Often peptides will have the phosphorylation on different serines in the same peptide. And if they're on one serine versus the other, they will have the exact same mass because just the location of the serine shifting, but they oftentimes will have different ion mobilities because maybe the serine's on this side, maybe it's on this side in the peptide, and they will often have a different collisional cross-section, which is what they're called. So they'll have a different shape, and so they'll separate in the ion mobility space. But if they're from the same molecule, they will elute in the same ion mobility. And we could actually use ion mobility to determine different isoforms of the same peptide with the same mass, which is actually really cool. All right, so many times we can detect peptide elution groups that we can't quantify. So proteomics has gotten a lot more powerful over the last like 5 years, but it's also gotten a lot more intractable. So it used to be pretty easy to explain, like, what is the mass spectrometer doing? Like peptide spectrum matching, pretty easy to understand, even for people new to the field. But now that we're doing things completely differently, it is often intractable. So what is oftentimes the computer making these elution groups or doing this analysis? Think of it as like a really complex signal analysis. And the software is kind of like black boxy. We really don't know exactly what it's doing, although sometimes in publications and app notes and on YouTube, they kind of tell you kind of what it's doing. So oftentimes we can get a detection. So think of like we're detecting these really complex signals in a mass spectrum, and sometimes we can quantify them. So if the peak looks really nice, the signal looks really nice, we can take either the area under these peaks or the intensity at the max, the full width at half max, or the intensity at the max of the peak, and get a number out of it, right? And we use that number and we smoosh them together in different ways. We can do that for every single ion in the peak, and we sum them together or do clever things with them to get a number. Sometimes the peaks don't look very good. So sometimes we can detect a peptide, but quantifying it can be a little bit more difficult. So surprisingly, this is a real detection, and I believe it. So you can see these peptides, fragments are at the top, and the MS, these group of ions are all eluting together at the retention time that we're predicting, and probably, maybe, this is kind of hard to tell, at ratios that we're predicting to. Can we quantify this? Maybe. Is it useful quantitation? I don't know. So I like to think of it this way, like we have a dynamic range of about 10 to the 4th, maybe a little more, maybe 10 to the 5th in the mass spectrometer, probably 10 to the 4th. And so let's say this is, this has an area of 10,000 or something, and I'm just guessing because my eyes aren't good enough to see this, see this slide. So let's say this has an area over intensity or whatever, how we're calculating all of these ions together, of 10,000. And let's say this one has an area and intensity of 50. Is that really going to add, when you sum them all together, is that really going to add much noise or much quantitative differences if this was wrong? Let's say this was wrong and we add it we say it's a peptide and we add it to our protein. Is it going to really add much to it? Maybe not. Maybe if we have 15 or 20 of these, could. So even if they look kind of crappy, they may not add to the overall noise of your protein group quantitation, I think. Okay. All right, so just an aside, we used to identify peptides by their MS2 spectra, like maybe post 2017, 2018. And now you could think of it as, so back in the day, this was called peptide spectrum matching, and I have a whole video on this, which is kind of out of date. So now, don't think of it as peptide spectrum matching. Think of them as detections. So there's a ton of analytes in our solution we're putting into the mass spectrometer. We're seeing if we could detect them using artificial intelligence, deep learning based strategies, and maybe some different statistics. But basically, they're either deep learning or traditional machine learning technologies that can figure out physiochemical characteristics of these peptides, like what are their masses are easy, but what are the intensities of the fragments? What are the retention times? What's the collisional cross section or ion mobility, for example? And using all of these things, we can now detect them much easier than we could have before. Okay, so what are we measuring? So this is kind of going to help you with SpectraNet, I hope. So for example, let's say SpectraNet says this is a precursor. So a precursor could be an MS1 ion with 2 protons, but it can also exist in more than one precursor. So this is also the same peptide with the MS2 fragment precursors with 2 protons. This would be, combine those all together and we get an elution group for a +2 precursor. You could do the same thing for the +3 precursor. So just the same peptide, but now instead of 2 protons, we have 3. And remember, we're measuring mass overcharge, so those mass overcharge is going to be different. And we can do that for the intact mass of the peptide, the MS1 precursor for this 3 protons. And then we have the same with all the fragments, with 3 from this precursor. Fragments usually are singly, are not multiply charged. Sometimes they are. So this could be with 3 protons. I'll have to check if that is correct. So anyway, we get an elution group for that. We combine them all together, and we get a peptide. It's just PEP. So at this point, we've measured like 15 things, like 15 areas. So if you go back, why isn't this working? It won't let me go back. That's really strange. Okay, so anyway, it will, anyway, we have like maybe 7 to 15 different areas that are all summed up into this one number. So anyway, it's a lot of stuff. Okay, and then once we get the peptide quantity, we do some really clever things to group those all together into the protein quantity. And SpectraNet uses what's called ID Picker, and I put two links in this presentation, so you can go back and click on them and read all about it. And you can see it's actually quite complicated. All right, and then once we do that, if you have more than 2 samples, so we have to figure out how to do this in a robust way. So the problem here is that because we digest proteins into peptides and we analyze different samples, sometimes, and you can see this in this chart here, sometimes this sample will find this peptide and maybe this one, but another one will find these, and these are all from the same protein, or may find these. And this is because, you know, we take a very complex mixture of thousands of proteins, digest them in the 20, 50,000, 60,000 peptides, and not all samples will have the same number of peptides. So it's not a very robust way to just sum up those peptides, although it does work, per sample, because some samples will just find other peptides, maybe by chance, or maybe because there's less of it, maybe there's more of it. So anyway, people today use this algorithm called max LFQ. You have to read it like 3 or 4 times to really comprehend it. So here's the paper. I have to read it like every 3 months to really understand what's going on. But basically, it uses ratios of these peptides in different samples. And it usually needs at least 2. And then my face is kind of in the way. But in the slide, you could see, and then it uses some linear algebra approaches to take the total signal and spread it out over all of the samples. I believe that's what it's doing. So anyway, you could read about max LFQ and maybe read it every couple months to really remember.